Alright, so now that we can find critical values using one of the three cases, the next step then is to determine if the critical, just like with the one variable case, the next step is to determine when we have a relative max or relative min. Now with multivariable functions, we can only look at certain outcomes, and there's this very, very specific process that we go to, and it actually resembles the second derivative test, the concavity test. Alright, it has to do with the same kind of idea. Has the function turning in what direction, but in this case I have to check two different types, two different things. Alright, so there's actually it's a fairly lengthy process to determine relative extrema. Alright, so find relative extrema of functions with two variables. Again, not all critical values are extrema. Right? Just like the one variable case, some are max, some are mins, and some are neither. Right? They're just places where I've got a stopping point, but it's neither a max nor a min. Alright, what we use is what's called the second partials, or the Dtest. And the reason why is because there's a D formula that you have to use that tells me if the critical value is turning, right? Meaning I'm going to either get a max or a min, or not turning, right? It's either just a stopping point. It either continues to decrease after it or before it, or increase, right? It doesn't turn directions. Right, so the first thing is you have to find the critical points, which we talked about in the last video. So I'm going to do an example here. Alright, so find the first order derivatives. If they're linear, you can use a matrix. If they're not linear, alright, you'd have to use substitution. And then if there's the other case where it's not, you just solve for x, solve for y. Alright, so this example, if you want to see where the numbers come from, you'd actually solve this one by substitution. Alright, you'd substitute, and then you'd have to factor. And you get 3 critical points. And this function has a critical point at 0, 0, negative 2, 4, and 5, 25. Alright, so it's three places where I could have possible max mins, or neither. Alright, so to determine if those 3 points are max, mins, or neither, there's a process. Alright, the first thing is I need my second, that's why it's called also the second partial test. The D-test is because we put the partials in a D formula. I only need 3 partial derivatives because the mixed partials are always the same, so I only need one of those. So I need the second derivative with respect to x, twice. The second derivative with respect to y, twice. And then we could do either one of the mixed derivatives, but just to keep it simple, we do the xy derivative. Alright, so in order to find those, I actually need to write down my first derivatives. Alright, so my first order derivatives with respect to x is going to give me a 12x squared plus 40x minus 4x to the xy. With respect to y, 2y minus 2x squared. Alright, those are my first order derivatives. And now I find my second order derivatives. Again, I'm only going to find 3 of them because the mixed derivatives are the same. Alright, so the second derivative with respect to x, I'm looking here first, so I'm going to get a 24x plus 40 minus 4y. With respect to y, comes out negative 4x. Alright, now I'm looking here to find this one, so that comes out just 2. Alright, that's an easy one. Alright, so there are my second partials that I need. Second derivative with respect to x twice, y twice, and then one of the mixed derivatives, which again, just to keep it simple, we do the xy derivative. You could technically do the yx, but again, we like to keep it simple, so we set it up that way. Alright, so where we put these is this is where and it does have to do a little bit with concavity, it has to do with how it turns. But we put them in the D formula. Right, the D formula is, I take the second derivative with respect to x times the second derivative with respect to y minus the mixed partial squared. Alright, so for our example above, my second derivative with respect to x, so my D formula, would be 24x plus 40 minus 4y times 2, right? Let me double check and make sure I remembered those correctly. 24x plus 40 minus 4y times 2 minus the mixed derivative squared. The mixed derivative was a negative 4. And make sure you're careful. It's the entire function negative 4x squared. And so if I go to simplify, you don't have to simplify it. But since I'm going to plug points into it, I just think it's easier. So I'm going to multiply through by the 2. So this is going to come out 48x plus 80 minus 8y. And then this is where you have to be really, really careful. It's negative 4 squared, right? Remember, this really means negative 4x times negative 4x, right? So it's negative 4 times negative 4, which comes out 16. X times x, which gives me out my x squared. All right, and so you're only squaring this part, this negative state. So 16x squared is what that squares out to be. All right, I can't do anything more with that. There's no like terms, so there is my D formula. And what the D formula does is it has to do with, there are two ways we can be concave. We could be concave in the x direction and concave in the y direction. And if the concavities are the same, we turn. Right? I'll turn one way or the other. If the concavities are conflicting, well then it's not a turning point. All right? And so that's what the D formula tells us. And so that's what we have to do first. So to figure out if my critical values are turning points, I plug them into the D formula. All right, so the first thing you do is you plug them into that D expression. So I take my x value and my y value and I plug them into that D formula. If the D formula comes out positive, and all that's telling me is that it does turn. I don't know which direction it turns yet, but it tells me it's either turning and giving me a maximum or turning and giving me a minimum. Now I have to check which direction it's turning by looking at one of my second derivatives with respect to a variable. And again, you could look at either one. We just stick with the xx to keep it simple. All right, so once you plug it in, if the D formula comes out positive at that point, then it's either a max or a min, one or the other. It's turning. I have to do a second check or test to figure out how it's turning. Is it turning up, giving me a minimum, or is it turning down and giving me a maximum? All right, so once my D formula comes out positive, and then there's two checks. If the second derivative is coming out negative, when I plug my point into that, the second derivative, and again, we do the second derivative with respect to x, so if f sub xx at my critical point AB comes out negative. If the D formula came out positive, well, that means the second derivative with respect to y should also come out in the same, right? It should be turning the same way. You only have to check one of them, and so just to make life simple, we pick the xx to test. But what this has to do is, well, this is telling me how it's turning, right? If the second derivative is negative, then it's concave down, right? It's concave down, and actually it's concave down in both directions. And so that's where we get a relative max, all right, at the point AB. If the second derivative, so my D came out positive, meaning it's turning the same direction for both variables. If my D-test comes out positive, so again, we keep it simple by doing the xx, but technically speaking, the y should be exactly the same. Should also be positive. Now, it might be a different number, but it should also come out positive. All right, positive tells me that it's concave up. Well, it'll be concave up in both directions, and so it would have this sort of three-dimensional shape, which means this would give me a relative minimum. All right, so the D tells me it's turning the same way. Tells me it's turning. I have to check one of the variables, xx or yy. And again, just to keep it simple, we say xx, but technically could check yy. All right, if it's positive, I get a minimum because it's up, concave up. If it's negative, I get a maximum, concave down. And again, the way this relates, the best way to relate it to is the second derivative when we have the one variable case. All right, so that's if the D comes out positive. Well, what happens if the D comes out negative? So if you plug your critical value into the D formula and it comes out negative, this is actually easier because you're done. You don't have to check anything else. If the D formula comes out negative, we call it a saddle point because that's the shape that comes out. And it's not an extreme. It's not a turning point, right? Which means it's neither a max or a min. It's just a critical value. Right? The reason why, when the D comes out negative, that means I've got conflicting concavities. So one direction it's concave up, the other direction it's concave down. And so what happens is in your three, and again, it's a little hard to see on a two-dimensional plane. If you look at the MyLab video, they show the better picture of it. But what happens there is it's not a peak or a valley, right? It's not a peak, which would give me a maximum. It's not a valley that would give me a minimum. The shape that literally comes out is sort of a saddle, a riding saddle, and that's why they call it a saddle point. Alright, so this would be a saddle point, and we call it that because of the shape. It's a critical, but not an extrema, meaning it doesn't turn up, doesn't turn down, doesn't give me a max, doesn't give me a min. It's a critical, which is still kind of important, and it would have something to do with inflection points, but again, we don't do that in this class. Alright, so let's do our example that I had before. Remember, I had 3 points. I had found my D formula. If you remember, if I'm going to go back and look at my D formula, it was 48x plus 80 minus 8y minus 16x squared. Alright, there was the D formula for that function. Alright, so what you do is, well, you test each point. Test each point. So, testing negative 2, 4 first. So, finding the negative 2, 4 plug. So, again, I'm plugging it into this D expression. So, I get 48 times negative 2 plus 80 minus 8 times 4. 16 times negative 2 squared. Alright. Well, what does it come out to be? It actually comes out a negative 112. Well, that means it's less than 0. And so that tells me I've got conflicting concavities. And so I'm done. I don't have to do any more work. Alright, the test came out negative. Negative D test, which tells me the negative 2, 4 is a saddle point, which means it's a critical, but not an extreme. It's not a max nor a min. Alright, so negative 2, 4 was a saddle point. Alright, now I'm going to test the second point, which is the 0, 0. 0, 0 is always a nice point because it basically zeroes out. That's gone, that's gone, that's gone, and so I'm just left with 80. Alright, well now, D came out positive. Alright, but I'm not done yet. There's a second step to coming out positive. It came out positive. The second step is to check, alright, this tells me it is a turning point at 0, 0. Now I have to figure out which way it turns. And again, the rule of thumb is to use XX, but you could technically use YY. Since we, so if you remember, XX was, 24 something, I can't remember. 24x plus 40 minus 4y, and remember f of yy was 2. You'll see that they both will give me the same thing. If I plug my 0, 0 into the xx, zeros out, leaves me with 40, which is positive. Well, this is 2, which is positive. That tells me, it's a turning point. This tells me how it turns. Since it's positive, it's turning up. So it's turning up, which makes it a relative minimum. At that value, I'd have to plug it into the original function to figure out what the minimum was. Alright, but I know that I have a minimum at 0, 0. Alright, so 0, 0 gives me out a minimum. So the last point I test was the 525. Alright, so again, I take my 525, plug it into the D formula. So I get 48 times 5 plus 80 minus 8 times 25 minus 16 times 5 squared. Comes out negative 280. Alright, so we've got one minimum, and then the other two were saddle points. And a lot of times, because they're complex functions, actually saddle points are fairly common. Alright, so 525 is just a critical point. That's a saddle point. It's neither max nor min, it's a saddle. Alright, we're going to practice this more in the next examples.